I wanted to today to tie this class, loop this class back into chemistry. And I know we've kind of gone off on tangents sometimes, and I want to bring this class, our molecular orbital discussion, back to a grounded position that we're comfortable with, finding something that we have in common with regular chemistry, if you will. So what we're going to do today is talk about methane. Right? We're basically going to do molecular orbital theory for organic chemistry, introduce that to bring us back to kind of a common ground where we've dug very, very deeply into atoms and molecules today or this year, and now I'm going to kind of bring us back out and bring us back to reality. Of course, I have an interesting experiment that I'll show you at the end if we have some time that came out last year. People are still learning things about methane. It has very, very interesting electronic structure. So what I want to introduce to you today is, first of all, we're going to learn about hybridization, right? You know, this idea of methane having sp3 hybrid orbitals. I want to introduce that concept to you today and talk a little bit about methane. One of the things that's very interesting about methane is, and this is where molecular orbital theory really teaches us the intricacies of structure that you don't really get to appreciate just by looking at sticks and balls. But you know, one of the things that we know and love about methane is that it has 4 equivalent carbon-hydrogen bonds, right? We have 4 equivalent. I'm sorry, that's not supposed to be a 4. That's supposed to be a 4 equivalent CH bonds. Tetrahedral, right? It's got tetrahedral geometry. Right, which means that the angle between a hydrogen, carbon, hydrogen, the hydrogen-hydrogen bond angle is 109.5 degrees, right? You guys know all this stuff. You've seen this before, right? But the idea is that you have 4 equivalent bonds, and we represent, so the CH bonds represented by what we call sp3 hybridized orbitals. Right, and I'll talk a little bit about what hybridization means today. Right, the idea of sp3 hybridization is very, very simple. Right, if we think about carbon's electron configuration, right, a neutral carbon atom is 1s2, 2s2, 2p2, excuse me. Right, and so we have, the idea, of course, is the way we are going to construct this is that we have a 2s orbital that looks like a sphere that's got 2 electrons in it. And then we have 3 equivalent p orbitals that are different directions. And there's 2 of them have half-filled shells. We can call this a px, py, and pz, whatever you want to think about them. Right, and these, of course, have the classic symbol, the classic design. And again, I'm not being consistent about my orientations. It doesn't really matter in this case, right? And so, you know, if we're going to create 4 equivalent CH bonds, right, we know what we get out, right? We get out the exact same bonding structure for every atom. But, you know, if we just add these carbon orbitals naively to hydrogen 1s orbitals, right? We take hydrogen 1s orbital and add it here, and add it here, and add it here. Right? It's not really clear how you get 4 equivalent bonds. Right? Because you're going to have something that's along the y, something along the x, and you got this s plus s interaction. They don't really look equivalent. Okay, so, but we know that they become equivalent. So the way that we instead represent this system is we construct a new set of orbitals, right? What we do is an intermediate step where we transform these carbon orbitals into an equivalent set of what we call sp3 orbitals. So we do an intermediate step transformation. So an intermediate transformation where we add a little bit of S to each of the P's. Okay, and we're free to do that. Of course, again, what we're doing is we're trying to empirically construct a set of orbitals that give us the design or the structure that we want. All right, I know a priori that methane is tetrahedral. It transforms like a tetrahedron. So I just need to come up with a really simple way to adjust my carbon orbitals, put them in an orientation that gives me the correct answer for experiments. Okay, so again, I'm not doing anything particularly. I'm not predicting without experiment that they should be tetrahedral. There's nothing to expect that. We just know that it is. So the best way to do that is to combine. Basically, what happens is the S. Remember, the S's and the P's for most atoms, they're all about the same energy. In hydrogen, they're exact same energy. And so you can add and subtract combinations. These orbitals can mix together in order to form a set of new orbitals that maximize the distance between each of the electrons. Right? Because what we want to do is we want to take each of these electrons and bond them to one of the hydrogens, and we need to arrange them in such a way that all of them are maximally distant away from each other. Right? That's what atoms are going to want to do. They're going to want to stay as far apart as possible, right, to reduce repulsion. And the way they do that is that the S's and the P's mix together a little bit. And in fact, they mix together in a very nice way. They mix together where we mix 25% S and 75% P. All right, so we take a little bit, each of the P orbitals, and add just a little bit of S to them. And you get 4 equivalent orbitals that look like this. All right, so when you add an S to each of the P's, you end up getting kind of a fat lobe and then a smaller lobe like this. Right, and each one of them is equivalent. They're just pointed in different directions. And there's 4 of them, right? We put in 4 atomic orbitals. We mix them together, mold them together with like putty, and we get 4 new ones out. And of course, and we get 4, the idea is that we get 4 equivalent ones that are all along different directions of the tetrahedron. And I'll show you a better picture of the tetrahedron in a second. Right, so each of these are going to have 1 electron. Right, and these are our sp3 orbitals. All right, of course, the question, of course, is I've added these in such a way, again, once I told you, how do I know these are tetrahedral? Right, but one of the things that we have to do is we need to construct the orbitals in such a way that give us a set of orbitals that are tetrahedrally symmetric. Right? The orbitals also have to look like a tetrahedron. And there's a really nice way to think about sp3 orbitals. I like to draw them like this. There's a better way. Let me put a better way to think about how these things, how it forms, or rather, let me think about how methane forms in a tetrahedral way. And the way to think about tetrahedrons again is to think about cubes. Right? Tetrahedron things can be embedded inside of a cube. So another approach right? This is we get our hybrid orbitals from this. This is more of a visual way to generate it. Is we're going to add 4 hydrogen 1s orbitals to the 2s and 2p orbitals of carbon. All right? And we'll see very naturally where the sp3, the tetrahedral symmetry, comes from when we do it this way. All right, so what I'm going to show you is this. So let's just look at, all right, so we want to put 4, we know we want to put 4 hydrogen atoms in tetrahedral symmetry, right? We know that they're tetrahedral. So what I'm going to do is I'm going to build a cube. Right, so there's my cube. And what I'm going to do is I'm going to place hydrogens at the edges of this cube. All right, we need to put 4, and we need to put them in tetrahedral symmetry, which means that we're going to put one hydrogen at this edge. So this is a hydrogen. We're going to put another one over here on this edge. And we're going to place the next 2 at their equivalent spots for tetrahedral geometry, which is here and up here in the front. Okay, so there's my 4 hydrogens at these 4 edges of the cube. We have 2 in one plane and 2 in another plane. It's not too hard to show for a little geometry. This has tetrahedral symmetry. This is how a tetrahedron embeds into a square. And now where does the carbon go? Well, we're going to put the carbon right smack in the middle. Right, so let's first do a 2s orbital. Right, so we're going to add a carbon 2s plus 4 hydrogen 1s orbitals, and we want to add them in a way that minimizes the energy, right? We want to think about the bonding contributions, right? The bonding orbitals for methane. So we're going to want to minimize the number of nodes. We want to maximize the overlap. So again, I'm just going to make sure that we have everything with the right sign. These are pluses. Right? These have plus signage, and what we're going to do is just put a fat carbon 2s orbital in the middle. Right? And this is also plus. Right? That's our carbon atom. I'll clean this up a little bit. Right? This is our carbon 2s orbital. Okay, and if I draw bonds, right? If I just draw little bonds here, it's not too hard to see that this is methane. Right? This looks like this has that tetrahedral symmetry that methane has. Right? We just embedded it on a cube, inside of a cube. All right, so we have this really nice bonding interaction, right? Everything has positives, right? And of course, I can change the signs of these individually if I wanted. There's only certain numbers of ways to do it because you have to maintain tetrahedral symmetry. I can't just turn everything off and get a new orbital. It has to be tetrahedral, which means that when I replace one atom with another one along the tetrahedral symmetry, I get the same orbital back. They have to maintain the symmetry. This naturally maintains the symmetry. Everything's positive. This is a beautiful bonding orbital, right? Everything is adding constructively, right? So we already get one bonding orbital here. Right? And it's spherically symmetric, right? It's positive, right? Every direction you look, it's the same sign. We've added things very nicely together. It has kind of symmetric, very spherically symmetric symmetry to it. Right, so this is a very low-lying orbital. This is stable. This is a strong bonding orbital. No nodes. All right, but we have to also add our p orbitals too as well, right? Our hybridization scheme requires us to bring the s's in and the p's. So what I'm going to do now is I'm going to bring the p's in here. We're going to take this s out and put a p inside and think about how the p's interact with these hydrogens. So let me draw a couple more boxes. I'm going to draw 3 more, one for each p orbital. And again, if you find an easier way to quickly draw these, that's fine. I just think it's easier to see things in cubes. And we'll do one more. All right, the way I'm going to tackle this, we know where the hydrogens lie. All right, there's my other cube. Okay. So we know where the hydrogens lie. So we know that there's always going to be, I'm going to keep them in the same place, all right? So we're going to draw our hydrogens in the same place. All right? So they're embedded at the edges of this lattice in the same place. Right? And what I want to do is I want to add my p orbital inside of here. Right? And I want to calculate, I want to figure out the way to make the signs of each of my orbitals so that I maximize the bonding interaction between the p that I'm going to put inside of there and the s's for the hydrogens. Okay? So again, there are multiple ways to combine signs. Some are going to be higher energy than others. They'll have less bonding character. They'll be higher energy. There might be the anti-bonding combinations. And I'm only concerned about the bonding combinations for now. So let's go ahead and put in our 3p orbitals. It doesn't really matter how we do it. So here's one that may be in this direction. We put another one in this direction in the center. And then, of course, the other one is in and out of the plane, like that. Okay. So what we want to do is we want to add the p's and the s's together to maximize or to minimize the number of nodes or maximize the bonding overlap. Okay, so one of the things about the p orbitals is that it has to change signs. Okay, so we have to assign signs to our p orbitals because they always have two different signs. So we could say, for instance, the yellow is the positive, and I'll make a negative here. Right, and we just have to choose an orientation. I'm just going to choose it like this, negative on this side, positive on this side. And then we'll do negative in the back here, and positive in the front. Okay, and what I want to do now is I want to choose the signs on my hydrogen atoms to maximize the bonding. All right, so this one's really easy to figure out, right? This is, if you think about a line being cut through the middle of the box horizontally, we have a nodal plane basically, right, through this edge, right? Right, there's a nodal, right? There's a plane of no probability here, right? So the sign of the wave function of the molecular orbital basically changes signs above and below this plane. So it's a really, really easy choice, right? We can just make all of these positive on the top, and then all of these negative on the bottom. Right? And we get a nice interaction here, and a nice interaction here. Like that. Okay? So this is a nice bonding combination, but again, we've introduced, right, there are no nodes here, right? There's no sign changes here. Right? Remember, sign changes imply that there are places where there is zero probability. Or if you think about waves, nodes means that your frequency, you're doing more than one period of your wave, and therefore higher frequency, therefore higher energy. So what we want to do is we want to make our waves look as lowest frequency as possible. They have basically as few nodes as possible. So this one has 0 nodes, everything's the same sign. This one obviously has one nodal plane, right? It cuts through the middle. Sign changes on the north side of the box versus the south side of the box. So this is also this is a bonding characteristic, but it's not as strong. It's a less stable bonding orbital because it has a nodal plane. Right? It has one node plane, one node. This is node, not mode. That's this plane right here where it changes sign. So this is higher energy than the one from before, but it's still bonding. Okay. And again, maybe it's not so hard to now see what's the difference between this one, and this one. The only difference is that I've rotated the system. Right? Because I can still draw a nodal plane here. Right? This instead now it's vertical. Right? It runs through the system like this. Okay. Stop it. Thank you. Right, you have this nodal plane right here. Right, and that gives us, once again, a very, very easy decision to make. Right? These two on the right are going to be positive. And these two on the left will be negative. And again, again, I don't really have to drive the point home too much. This one's a little trickier to draw. Oh boy, I don't know if I can draw this nodal plane. but the nodal plane kind of runs through the center of the board. Yeah, I'm not going to draw that. That's a tough one to draw. But you can see, again, we have a sign change. And the negative ones are going to be this one and this one, the ones on the back face of the cube. And then they're going to have two positive ones here on the front faces of the cube. All right, so these are our four. Again, once again, we still have one node for each of these, right? One nodal plane. They're all higher in energy than the S combination because, again, the sign changes, but they're all bonding. Right? We have a appreciable bonding, right? A constructive bonding between two hydrogen atoms and one lobe of the p orbital. And there's three of them. And again, it's not too hard to see this. If you move these boxes around, they're all equivalent to each other. They're just rotated along different axes. So all of these are precisely the same orbital. They're degenerate. They're a degenerate set, a trio, a triplet degenerate set. And that's actually a characteristic of tetrahedral molecules, this triplet set. Right? So this is what's called the tetrahedral orbitals. Right? And there's three of them. All degenerate. Right? So they all have the same energy. All right, so here's the interesting thing. All right, this is the thing that kind of very, very interesting about how this comes together. Okay, so when we do the old school hybridization scheme where we add 25% of hydrogen, 25% S and 75% P to make four equivalent orbitals. And again, all I need to do is just add little hydrogens to the ends of these. Right, let me do it a different color, sorry. I can add little hydrogens to the ends of these lobes if I wanted. Right, this is where the hydrogens will come in. Right, and then these fill up with the hydrogen electrons. But now here's the problem with these two arrangements. All right, we have different results. Right? This construction that I did up here implies that I form four equivalent bonds that each have two electrons in them. And they're all the same, right? The only difference between each of these combinations is the way that we've rotated, right? It's just they're all rotated in a slightly different way. Right? But once again, they should all be the same. All right? So what I predict from this calculation up here, right here, is that I should get four equivalent molecular orbitals, all at the same energy. But when I look at this construction, where I've taken to my advantage the tetrahedral geometry of the molecule, right? Up here I've done something very naive, right? I've just added them together, mixed them together, and formed four equivalent orbitals, and I get four results, but they're all the same energy. They all look exactly the same. They're just rotated slightly. But when I construct the system and I consider the actual tetrahedral geometry of methane, I get two classes of orbitals, right? I get this full, even, spherically symmetric addition of the carbon and the hydrogen and hydrogens. And then I get a different set of higher energy orbitals that are all equivalent and degenerate. So there I get four of the same, and here I get two classes. One orbital by itself at low energy, and three that are all the same energy at higher energy. So the difference between these two molecular orbital diagrams, if I were to then construct it, right, this one here, the one on the top, right, this gives me something that looks like this, right? I would expect to have four equivalent molecular orbitals, each with two electrons in them to give me my octet. Right? So all of them have the same energy. And then here in methane, I'm just going to kind of dram it off to the side. I would get one low energy and then 3 at higher energy, and each of these are completely filled. All right, so I have 2 competing predictions. And I don't know which one's right and which one's wrong. Okay, but it doesn't seem like either one is an unreasonable approach. I get 2 different predictions, right? This implies that they're all the same, so when I would only expect to see 1 peak when I ionize the molecule and remove an electron. But here I would expect to see 2 peaks for the ionization spectrum, 1 for these electrons and 1 for this electron. Very, very different. And so let's go look at the data. Right? 2 different ways to look at tetrahedral symmetry, with 2 potentially. One of them has to be wrong, of course, right? The spectroscopy will tell us the truth, and one of these is going to end up being incorrect, and it's not exactly clear why that is, right? But this is kind of what you learn in Gen Chem, of course, right? You just mix the orbitals together, and they all make equivalent. You add hydrogens, right? The way you would learn, right, when you think about methane, it's got 4 equivalent bonds. You think it would have, it's reasonable to assume that it has 4 equivalent molecular orbitals. All the electrons are exactly the same, right? Very nice high symmetry system. But this predicts that the electrons are 2 different types of electrons in methane. There's these deep ones that are very strongly bound, and then you've got this series of bonding orbitals that have p-like character. All right, so let's figure out which one's right and which one's wrong. All right, so what I'm going to show you, if I can find it, let's look. That was not the best picture. Let me pull up a picture. Ah, this is beautiful. All right, so then what I'm going to do, again, if you've worked on the homework, you've seen this idea of, oops, there goes my, sorry about that. Thankfully, I saved it. If you've worked on the homework, you've seen this idea of photoelectron spectroscopy. The idea that you're going to shine a light at the molecule, very high amount of light. Methane will kick an electron off, and then you'll see an absorption for each of the electrons that you kick off. Sorry, let me just bring this back over. All right, so let's go look at the spectrum. Okay, so we have 2 predictions. One gives us 1 peak, because there's only 1 type of electron. The other one gives us 2 peaks. So here's a very generic picture of the photoelectron spectrum of methane that I just pulled off the internet. And voila, it has 2 peaks. So there's a deeply bound peak here at about 23 eV. Right? Ionization potential is, again, how much energy it takes to remove an electron. There's this deeply bound one at 23 eV, and then there's something around 14 eV, kind of near the hydrogen carbon 2p energies of the atoms. So we have a very, very strong bonding orbital, molecular orbital, very, very strong bonding one, and one that's slightly less bound. And as you can tell, one has a lot more electrons than the other. The intensities are meaningful. Right? In fact, if we look at the intensities in particular, we look at if we just kind of fit this peak here, like as a peak, right? And we look at these intensities, and we measure the ratio of these peaks. Right? The peak difference is about 3 to 1. Hey, that's interesting. Didn't we just have a 3 to 1 combination? Right? Didn't we just see that? Right? So the photoelectron spectrum, so spectroscopy says 2 types of electrons. And are 2 types of molecular orbitals, if you will, bonding of molecular orbitals, and one has 3 times more electrons. Well, that sure sounds like our second prediction, doesn't it? And in fact, that's exactly the thing. It is, in fact, there are 2 different types of electrons. Not all of the bonding electrons in methane are equivalent. Right? This is not implied, it's not tetrahedral. In fact, the construction the very, very naive construction we made where we just mix a little S and the P's together, we did not take into account that these orbitals are symmetric, tetrahedrally symmetric. Let me tell you what I mean by that. Right? So we'll go back to our pictures in a second. The problem, let me just write it down. The problem with the naive construction, 25%, 75% construction, is that these orbitals do not reflect the tetrahedral symmetry of methane. If you've taken inorganic chemistry, you've probably learned about point groups. Especially if you're taking a Dr. Palenko this semester, I assume he's taught you point group theory. Maybe you have an appreciation for this idea that the orbitals, that your molecular orbitals in your electronic structure also have to have the same properties that the geometry have in terms of the symmetry. What do I mean by that? Well, let me just go back really quickly, right? What do I mean by tetrahedral symmetry, right? Well, there are certain operations I can do to this molecule. It's very easy to see in 1s where I can rotate the molecule. I can either mirror it, I can rotate it along one of the axes, all sorts of different ways to do this. And there's a series of transformations, different rotations and stuff that when I do this, I get the same thing out, right? What I do is I permute the hydrogens, right? I could, for instance, right, you can think about rotating this a bit so that this goes here, this one goes here, this one goes here, right? And you permute the hydrogens and you just get the same thing back, right? This is what I mean by having something having tetrahedral symmetry, is that there are a set of allowed transformations that take the molecule from one position to an equivalent one, okay? And there's a certain set of class of rotations and reflections that do that, okay? And so every orbital of a tetrahedral molecule, if a molecule is tetrahedral itself, every orbital of it itself has to satisfy at least a class of those allowed transformations. It doesn't have to have all of them, but together they all have to together. So I'm not going to go into too much detail about that. We obviously don't have time to do point group symmetry. But the idea is that the orbitals themselves also have to show that same tetrahedral symmetry that methane does. And as you can see here, again, this just looks like methane. It has the symmetry of methane. This does as well, this does as well, this does as well. Right? It's not too hard to show that you get, with a little bit of work, it's not too hard to show that all of these are valid under the symmetry requirements of a tetrahedral structure. They have the same symmetry elements of the molecule itself. What about those orbitals? Not at all, right? It's very hard to, right? The way that I've constructed these, imagine I rotate any one of them by 180 degrees, I don't get the same thing back. I've rotated 180 degrees. So I haven't permuted any of the hydrogens together, right? Because each one of these orbitals contains only one hydrogen and one sp3 hybrid orbital of the carbon. All right, so there's no way for me to ever take one of these orbitals and move it around and rotate it and transform it and permute the hydrogens because each orbital only contains one hydrogen. Right? They're basically lines, right? These have the symmetry of lines, not the symmetry of tetrahedrons. They're cylinders, effectively. So this cannot be the proper way to combine the orbitals together. All right? So what Pauling, actually this was done by Linus Pauling a long, long time ago, way before he won his first of his 2 Nobel Prizes. What he realized is that there's another intermediate step you have to take for this, right? This gives you the equivalence that you want, but it doesn't give you the tetrahedral symmetry. So what Pauling realized you have to do, and Mulliken and all the other old molecular orbital guys, is that you have to take these orbitals and add them together to get these, right? So you have to symmetrize these very, very naive constructions to get the symmetry of the tetrahedron that you need for the orbital to show the right behavior. So this construction that we did here inside the cube is perfect. Right? We came up with, we put our original atomic orbitals in there, and we came up with what are the best ways to combine the hydrogen and the carbon orbitals together to maximize bonding in a cube like this. enforcing a tetrahedral symmetry of the hydrogens by putting them in these corners, and we get 4 orbitals out of the proper symmetry. We get a singlet, very, very strong bonding orbital that has very strong S character. Of course, it has some P, right? In reality, these have S and P together. They're sp3. And then we get 3 p-type interactions like this that are slightly higher in energy, but they're triply degenerate. And this is exactly what methane shows. So this very, very intermediate, very naive transformation, we're just missing the next step. Ultimately, no matter what we do, we always end up with these 4. This is what the sp3 hybrid orbitals for methane looks like. Right? This is what we mean by equivalence. Obviously, they're not equivalent orbitals. Right? They have different energies. But the combination of these 4 together are the fingerprint for tetrahedral symmetry. This is what it means to have 4 equivalent tetrahedral bonds. It means you have to have orbitals of this symmetry. One fully symmetric and then this odd symmetry triplet, if you will, for p-orbites. Right, so the idea of equivalence is not so cut and dry. All right, so if we were going to put this all together now, so let me go back to the next page. Right, so we have, once again, we have indications from our spectroscopy. This is exactly the ordering, the structure that we predict. Right, we have a set of higher lying orbitals that have 3 times as many electrons, and a very deeply lying bonding orbital with 1 equivalent set of electrons, 1 pair. Right, so if we were to take this information and put it together and build an orbital diagram, right, so let's do that. So on the left-hand side, I'm going to put carbon. Again, we'll do energy in this order. Energy is on this order. Right, and then we'll put our 4 hydrogens on the right-hand side, and then our CH4 orbitals in the middle. All right, we're going to do the same construction that we did in our boxes. So we'll start with our 2s orbitals for hydrogen, or for carbon, sorry. These are at minus 22 eV. Okay. And then we have our p orbitals, which are at minus 12 roughly. I'll just put them like this. These are at minus 12 or minus 11.7. Right? And there are 2 electrons in these. 2 electrons. Okay. And then we have 4 hydrogens over there, right? And this is the key, is that we're not adding each hydrogen separately to the carbon. We're adding all 4 of them together. Right? Remember, go back to our orbital constructions. Right? We're not actually adding 4 hydrogens individually to each of the carbon orbitals. We're adding 4 of them together. Right? We have a pair that looks like this, and then we have this set, and then we have this set and this set of hydrogens. Right? So what we've done implicitly is hybridize our hydrogens together and then added the carbon to it. So we have 4 sets of hydrogen 4 orbitals, if you will, H4 orbitals. And they're at basically the same energy. They're minus 13.6. So we have our hydrogen orbitals. There's going to be 4 of them, right? And there's going to be 1 that's lower energy. Right? That's so we're all the same. And then we're going to have a triplet. Like that. And these are roughly minus 13.5. Okay. And these are called the T2 orbitals, and this one's called the A1 orbital. And they each have a hydrogen or electron in them, right? Each one has an electron in it, right? Each hydrogen brings in 1 electron. And I'll just sketch these out really quickly, the A and the T2 combinations. They're literally just the hydrogen atoms at the edges of our cube. Right, so I'll just draw them over here. So A1 for the hydrogen looks like this. We have our hydrogen here, and then we have hydrogen in and out of the plane, and they're all the same sign. Right, so that's our combination of our s orbitals together and our lowest energy set, and then the T2s. Again, let me just draw the stick figures again. Right, we got 3 of them. And the only difference between them is which ones change signs, right? So one of them is, so what I'll do is I'll draw the opposite sign a different color. So the first one, let me just make sure I got these right. So this one is here, yeah, and here. And I'll just do in different colors, here and here. I'll just color these in like that. And the other ones are negative. The next one will be here and here. And then we have hydrogens with opposite signs here. And then the final one is where the ones out of the plane are like this, and the other ones are like this. These are our 4 hydrogen orbitals, right? So what we've done is we've hybridized the hydrogens together, and then we've added it to the carbon. So it's a slightly different approach, but the advantage of this approach is that we've encapsulated the entire tetrahedral symmetry of the molecule. Everything makes sense. The hydrogens permute properly, and they add together. So remember, again, we know what the bonding orbitals we get are. The first one we get is a very, very deeply bound one, right, that has full spherical symmetry. Right, and it's a combination of the A1 with the 2s. Right, and of course there are 2 electrons that go in here. And this one is at about minus 23. Right here, right? This is, right, it's this one right here, the 23. And of course this makes a anti-bonding pair that is unoccupied. And it's actually quite high up in energy. Something like this. There's that bonding pair, and then what we make is we make a triplet set. Remember, we make a triply degenerate set of slightly less stabilized bonding orbitals, but they're still bonding orbitals. And as we can see, they're at about 15. Right? We're at 15 and 23, so we know exactly what energy they're at. So they're kind of like right here. 1, 2, 3. And again, these get, I'll do a different color. These are constructed from the triplet set of hydrogen orbitals and the p orbitals from carbon. And we make an anti-bonding set that has the same symmetry up here. Okay, and then all we do is we just fill in the electrons. We have 6 more electrons to fill. Right, and these are at minus, this is at 15 eV, minus 15 eV. Right? There we go. That's methane. Right? Methane. I found this was really, I don't want to call it mind-blowing. It wasn't that mind-blowing, but you know, I went through organic chemistry understanding these bonds, right? The way that we look at them from a structural perspective is that each of the hydrogen atoms are attached equivalently to the carbon atom, which is exactly correct. But the electrons themselves do not show that behavior. The electrons themselves show 2 different types of classes of behavior. There's a fully symmetric set, and then a triply degenerate set of p-like orbitals, right? And this gives you, right? But the thing is that these aren't contradictory elements. These are indications of the exact same behavior. Have a molecule with tetrahedral symmetry, which means you have 4 equivalent bonds at 109.5 degrees. That necessitates absolutely that you get this orbital structure. They're one and the same. And the only reason to understand that is through the application of symmetry. Right? I wish we had more time to talk about symmetry. Well, if you take spectroscopy with me in the spring, if you're in 4+1, I'll talk about symmetry in that class. Because obviously it plays a giant role, right? This indication here is not an indication of an asymmetry. This is the absolute tell of symmetry. The system separates into 2 classes. That is only molecules that have tetrahedral symmetry do this. And let me show you, for the last 10 minutes or so, let me show you an interesting experiment from last year that probes this idea. So what I actually want to do is actually think about what happens to this molecule when I ionize it. Right? So now I have, right, so if I ionize the molecule, I have some options for where those electrons can remove. Right? I can remove them from here, and I can remove them from here. Right? And the question, of course, is how does the geometry change for methane when you remove an electron? Okay, so it's a very hard question to answer. But when you remove an electron, right, if we remove an electron from one of these orbitals, the electrons, remember the only reason why the electrons put themselves into this orientation is to minimize repulsion. Okay, so what happens when you remove an electron is we would expect the molecule to adjust a little bit, because now you're going to have an orbital, like if we remove one of these electrons, we're going to have a p-like orbital with a missing electron, and things are going to want to reisomerize a little bit, because now there's not as much repulsion anymore. But the question, of course, is, right, so this is a chemical and structural change, right, when you remove an electron from methane. And the question that's very interesting to ask is, what's the time scale of this? How long does it take for once you remove an electron? How long does it take? So if methane has to adjust it away from tetrahedral symmetry, its orbital structure is going to change. Right? Remember, if it's no longer tetrahedral symmetry, because the atoms can now move closer to that other p orbital with the single electron in it, because there's not as much repulsion, it's not going to be tetrahedral anymore. The ordering of the molecular orbitals will change when you ionize this molecule. And the question, of course, is how long does it take, that once you remove that electron, how long does it take for the molecule to change its molecular orbitals, to complete the reaction, if you will, the intramolecular rearrangement, to go from methane at tetrahedral symmetry to a slightly more spread out and relaxed methane once you remove an electron. Right, so let me show you a really cool study. So this came out in Science last year, out of Berkeley. And it's an absolutely gorgeous study, really, really beautiful spectroscopy. So this uses tabletop X-ray spectroscopy. Okay, so they use very high-powered ultraviolet lasers and visible lasers and they combine the photons together in what's called a nonlinear process. You can take two photons of 800 nanometers, for instance, and combine them together to make a new photon at 400 nanometers, at twice the energy. Right? It's called a second-order effect. You can do this multiple times to generate photons of higher and higher energy. Okay, so they use very, very bright ultraviolet, mostly visible photons, and they combine them together in special crystals to make X-rays. And let me show you what they do with these X-rays. So what they're going to do is they're going to create, what they've done is they've taken methane and they've ionized it. Right, so here's an orbital scheme for hydrogen, or for methane. Regular old methane here. All right, so what they've done is they've taken methane and they removed the electron from it. Okay, so let me draw it really quickly. Maybe it's better if I just take this picture and put it in my presentation instead. Let me just do that really quickly. Okay. Okay. So what these experimentalists have done. So again, this is the geometry of methane, right? We've got our triplet set of orbitals here. They each have 2 electrons in them. Here's our really, really strong 2s combination, right? The really strong bonding singlet. And this is the 1s orbital for the carbon, right? The really deep one here. Okay, so what they first do is they ionize one of the high-lying ones with what's called strong field ionization. Right? So the first step that they do is they take this electron out. Right? They kick this electron out of the p orbital. Okay? So what you do is you create what's called a hole. There's a hole there. Right? And then what they do now is they take an X-ray pulse. So they take it, well, so first they excite the electrons. They excite that electron to ionize of 800 nanometers. That's what removes that electron. The 800 nanometer pump. Right? So that removes the electron. And then what they do at some time delay relative to that pump, right? So they kick the electron off with their pump, and then they have an X-ray photon come in at 278 eV, right? To take one of these 1s electrons and put it up into that new hole. Okay, so they're promoting a 1s electron. This is a carbon 1s orbital, bonding orbital. They're kicking that electron and bringing it into that hole. Okay, and so it turns out, though, that this structure, right, they do this, we'll look at the distance between these two pumps, the pump and the probe. This is a two-color experiment, and they change the time delay. We'll look at what those time delays are. But the idea is that when you remove that first electron of the 800 nanometer pump, remember, because of the Bohr-Oppenheimer approximation, the nuclei don't move. Right? The electron leaves immediately. In fact, this pump, the ionization takes attoseconds. Right? It's much, much faster than a vibration. So once that electron is moved after step 1, the molecule looks like this. Right? This looks like methane, 195.5 degrees. But it turns out that methane radical, is actually twofold symmetric. It has a different structure that looks like this. All right? So this is, again, how methane, because it has missing electron, it's not as repelled by all those electrons anymore. It can rearrange. And CH4 plus, if you look at it after a long time, looks like this. Right? So the structure goes through this, and it goes through it takes about 10 femtoseconds. Right? This is 10 times 10 to the minus 15 seconds. Okay, so what they do is what they're going to do now is they're going to do this probe at a function of time as this molecule reisomerizes. Notice that when you're in this state, right? If imagine you wait long enough that the molecule is allowed to reisomerize. Okay, you wait 10 femtoseconds, 100 femtoseconds, something like that, and then you bring in the pump or the probe. Right, and as you can see, the probe, sorry, let me start over again. The molecular orbitals for this version look very different. Right, you break that symmetry. Right, you have instead just a sequence of orbitals instead of having a triplet. So you get a different orbital structure, and therefore that hole that was there that you created with the first pulse is now at a different energy, because now it's in this highest lying orbital. And it's at 281 eV. So if you do the X-ray immediately, it will absorb at 278 because the molecule hasn't had a chance to reisomerize. But if you wait long enough, it'll be at 281 because the molecule is reisomerized, right? Because of the Bohr-Oppenheimer approximation, right? Nuclear motion is uncoupled from electronic motion. So the nuclei are just moving on their own, but the electrons can move freely. And so the question, of course, is can you observe this change? Right? Maybe you've ever wondered how long does it take for a molecule to, once it reacts, how long does it take to equilibrate to its final structure? And the fact of the matter is that it only takes a couple hundred femtoseconds for most molecules. This is a very typical lifetime, very, very short. Right? It's about the order of a vibrational frequency, like the CH stretch. Right? But if we can make our delta T small enough, smaller than 10 femtoseconds, we may be able to track this structure as it goes from the unrelaxed version with an absorption at 278 to one at 281. Right? So we're going to watch the molecule isomerize in time. And there's a beautiful picture that they come up with. So they measure this with this mechanism. And let me just pull this over. No, I don't want to spoil the result. So anyway, they do this spectroscopy, and they get this beautiful result. Which one is this? This is experimental. We'll look at the experimental and the theory. Okay, so what we're looking here is the spectrum, the photoabsorption or the photoexcitation spectrum of the molecule as a function of time. Okay, so this time axis right here is the relative delay of the X-ray versus the visible photon, right? So the visible photon starts at t equals 0. It's at exactly t equals 0 on this plot. And the time that's actually listed is when the X-ray comes in. So they do it before and they do it after. Okay, we always do it in between. So they measure some right, if you do, this is basically X-ray first. And this is X-ray last. And so on. Okay, and so what do you see? Well, at less than 0 femtoseconds, you see nothing. If you look carefully at the early time, the negative time, there's very, very little absorption, right? So that the red is the change in absorption, right? OD, the optical depth. So as you can see, there's very, very little change in the spectrum at early time, and that's not surprising because the light hasn't come in to ionize the molecule. They haven't made CH4 yet. So methane doesn't see anything. This only works for this X-ray pulse only works for cations. So if you haven't made the cation, you don't get any absorption, right? So you hit t equals 0. This is where the X-ray and the pump are at the same time. Voila, we get some signal. Of course, the diagram. There we go. Right? Get some signal. And look at as you track it, right? So as we move on, we're delaying the X-ray pulse slightly longer and longer each time. And what happens? Well, the energy of the absorption starts at 278, right? That's what we see for tetrahedral CH4. But as we go along and delay the X-ray probe, okay, well, so much of that. Right, so this, let me just write that, right? So this is X-ray, this is ionization. It's not a very good color for that, I'm sorry. This is ionization here. Right, and what happens as the X-ray gets later and later, the absorption frequency rises. The energy of the absorption rises. What you're observing here is this molecule, the methane molecule, right? You initially ionize it at t equals 0. It's in this geometry. And then slowly but surely, by slowly I mean 10 femtoseconds, right? That's 10 trillionths of a second. 10 quadrillionths of a second, excuse me, 10 quadrillionths of a second. The molecule slowly isomerizes to this. And as you can see, the energy of that absorption increases until it plateaus at around 14 femtoseconds. Right? And this is indicative of the relaxed structure. Right? So what have they measured here? Well, they've measured that once you remove that electron, it takes exactly 14 femtoseconds for the methane cation to reisomerize to its final structure. Right? And as you can see, it kind of fluctuates a little bit after there, and it kind of drops down again and finds a new equilibrium value, right? And that's not really clear why that is, right? You would think that once it hits that relaxed point 14 femtoseconds, it'd be done. But as you can see, it oscillates back down again. But again, that's maybe not that surprising because what happens to this molecule, you put so much energy into it, that the electrons can cascade, they can move around, they're very fluxional, and so you get some kind of chaotic after effects, some aftershocks here, right? Some oscillatory effects, right? This is kind of like an aftershock, right? The system is still equilibrating and vibrating back and forth a little bit and trying to get relaxed. And this is theory over here on the right, and as you can see, theory shows exactly that, right? This is theory, and this is experiment. Right? There's no signal at negative time because again you haven't created the ion yet. It immediately turns on at 0 femtoseconds, and it slowly rises to about 15 femtoseconds to the final structure. And then there's some aftershocks after there as it starts to equilibrate and reaches thermodynamic value. Right? This is, now I don't know if you guys think this is cool or not, but I think this is super cool. Right. So we're literally, when this is one of the questions that I asked in PChem, or things that I thought of when I was a student. How long do things take in chemistry? Not reactions, but imagine you remove an electron from something. How long does it take to get to your final state, right? This is your initial state. This is your final state. You usually think of electrons being lost instantaneously, but it's never instantaneous, right? There's always some time scale. And what's the time scale? Well, here it's exactly 15 femtoseconds, right? And they're able to observe that completely in their experiment, right? The amazing thing about this experiment is the resolution, right? See, you have to be so precise, right? How do you tell the difference between when you have two laser pulses coming into the same spot? How much different they are? How do you tell time? How do you tell the difference? How do you have a stopwatch, right? In order to measure this on a stopwatch, you need precision let me see, this is on a normal stopwatch, right? You need 15 to 16 digits after the dot, 16 to 16 decimals to measure this time difference. Right? So maybe it's worth thinking about instead. So one of the things that's very interesting is that there's no literal way, there's literally no way to time this with time. Right? But we can take advantage of something very special with light, is that light moves at the same speed at all times. So we can convert from a short time to a distance. Right? So if we need to tell the difference between 14 femtoseconds, so our delta t, well, let's just say our delta t is about 1 femtosecond. Right? We want to step our experiment by about 1 femtosecond, which is 1 times 10 to the minus 15 seconds. All right, so how much, if we wanted to detect, what if we instead looked at these pulses and measured exactly when they hit a detector? Okay, and if we see that one shows up, right, and we make one detector slightly further away than the other, so there will be a time delay between the two. Each pulse is moving the same speed because it's the speed of light. But we move one detector for say the X-ray away, a little further away from the sample than the one for the optical pulse, the pump. Okay, so we just changed the distance, right? So what would that distance difference need to be? Well, the difference of the distances that's needed. So the idea here is, let me just kind of draw it exactly. So here's our methane in our box. Our X-rays go in this way. And then there's a detector here. And then we'll say that our optical pulse is coming in this way and comes out. And there's a detector here. And let's move one of the detectors. Let's have it on a stage, right? So that this one, let's say for instance, this one can move to a new spot up to delta D, right? And so if the pulses are 1 femtosecond apart, let's say these lengths are the same. Let me just write that. So let's say these are the same lengths. Let's say these are each 1 meter, for instance. So if they're both sent out at the same time, they'll both end up at the same time if they're at the same distance. But if there's a delay, we can catch them at the same time if we move the one that's delayed a little further, right? Or the one that's earlier with the box. We can move the box a little further away, so that the earlier pulse hits the same time as the X-ray one does, right? So if the optical, so if delta t, so let me write it like this. If delta t is positive, so that means then that the X-ray is later. That means that the optical is going to arrive first. Delta D needs to be positive as well. And if delta T is less than 0, we got to bring the other one in. All right, we want them to meet at the same time. Match distances so light hits at the same time. Right? seems like a really reasonable experiment, right? So what does the distance need to be? Well, if the speed of light's moving at the speed of light, right, the delta D for this is going to be, well, let's think about it. So the speed of light is the distance over time. So the distance we need is going to be c times delta t, right? The speed of light times the distance. And that's going to be roughly 3 times 10 to the 9. Sorry, 3 times 10 to the 9? No, sorry, 3 times 10 to the 8, excuse me. 3 times 10 to the 8 meters per second. Times 1 times 10 to the minus 15 seconds. Right? So the distance precision we need in order to measure femtosecond changes in time in the delay of 2 pulses is going to be on the order of 3 times 10 to the minus 6. Or sorry, 10 to the minus 7 meters. Right? And that's pretty small, right? That's 300 nanometers. Or 0.3 microns. Right? So you need there are different ways to get around this a little bit. But this is kind of the way that original femtosecond lasers, how we time things, is we have 2 pulses that arrive, and we want to arrive at roughly the same, we delay them, but we want them to show up on the detectors at the same time, so we move one of the detectors in order until they match up. Right? And that requires us to move by 300 nanometers at a time. That's pretty hard to do. It's not an easy experiment. There's a good reason why this won a Nobel, why these femtosecond experiments won a Nobel Prize. It's a very, very hard thing to do. There are better ways to do that. You can use wave mixing. You can take your 2 signals together and mix them together. And if they arrive at your mixer at the same time, they'll constructively interfere. And if they're out of sync, they'll destructively interfere. Okay, so that's typically the way people do it. So instead, people use wave properties, but basically you're doing the same thing. You're moving two things together until both of them arrive at their destination at the same time. And if they do that, then they constructively interfere and you get a signal, right? And you can actually get to this precision that way, right? It's the equivalent of having 300 nanometers of spatial precision, right? And so this is a very, very hard experiment to do. And it hasn't been possible until literally last year. This is the cutting edge of femtosecond spectroscopy on molecules. This isn't the fastest thing anyone's ever measured. So interestingly, people have looked at electron transfer, for instance, between atoms. That's on the order of 100 times faster than this, 100 attoseconds. I think the fastest time people have measured between 2 laser pulses is about 10 attoseconds, right? So that's 1,000 times faster than this. But there's almost no way to do any chemistry at that speed. That's almost faster than everything in chemistry. So you can't really measure anything useful in chemistry at that speed. Most interesting chemistry happens on the order of 10 to 100 femtoseconds. But this is what chemistry looks like at that time scale, right? You're observing molecules, perturbing molecules by removing electrons and watching them isomerize to their final state on this scale, time scale. Okay. So anyway, that's all I really have to say about this. I like this experiment. I think it's really cool. Actually, at the conference I go to in June, they're going to present on this, and I'm really excited about it. Anyway, that's all I have to say. So I think this kind of brings us back into organic chemistry. Right? We now understand hybrid orbitals and this idea of symmetry. Right? Go back and we start to appreciate organic chemistry at the graduate level and the advanced level. These things start to play a major role. Right? If you, for instance, take advanced organic chemistry with Dr. Trillo, if you aren't already in that class, you'll learn about the Diels-Alder reaction, or about photochemistry. Photochemistry in the Diels-Alder reaction is built around the orbitals, the molecular orbitals of carbon, hydrocarbons. Right? You need to understand the orbitals to understand the reactivity. Right? So I won't dig too much more deep into that, right? But I think this leads us onto a really good jumping spot where if you want to explore quantum chemistry at the organic level, at the macroscopic level, macromolecular level, you've got everything you need. Anyway, that's all I have for you guys. Thank you so much for this semester. Final homework's due next week. You know what my office hours are. Thank you all. Some of you I'll see you next semester. Some of you I'll never see again. Some of you I will see again, and some of you I won't be able to get rid of. That's okay. I appreciate your hard work, and have a lovely summer. Thank you all.
have a good one, Professor.
You too.
I'll probably see you on Friday. For
Okay, that's fine. I'll see you then.